You wake up tomorrow morning, you walk into your kitchen, and there's no table, no chair, no coffee mug, just a pile of gray sand on the floor. You say, "Coffee table," and the sand moves, slowly. Then all at once, it assembles. Legs, surface, grain, solid, real. You can put your mug on it. This isn't science fiction. This isn't CGI. This is the actual documented peer-reviewed scientific goal of a real project funded by Intel, born at Carnegie Mellon University, now involving research teams across 3 continents. And today, we're going deep. By the end of this video, you'll understand not just what Claytronics is, but why it might be one of the most consequential technologies humanity has ever designed, and what's actually standing between here and there. The concept begins with a building block. They call it a Catom, short for Claytronic Atom. Picture a sphere, smaller than a grain of sand in the final vision. But inside that sphere is a complete computer. It has a processor, memory, its own power source, a ring of tiny electromagnets, LEDs that can display any color, and a wireless radio to communicate with every neighboring Catom. In other words, it is a complete autonomous computing device that also happens to be physical and can connect to other identical devices and move. Now, scale that up. Imagine a billion of these Catoms in a single cubic meter of space. Every Catom talking to its neighbors, every Catom aware of its own position. The collective billion-strong ensemble receives a single instruction: become a chair. And the collective does. Not because each Catom knows the full shape, but because each one follows local rules, responds to local neighbors, and the global form emerges from the bottom up. No central controller, no foreman, pure distributed intelligence. The researchers at Carnegie Mellon had a name for this kind of material. They called it programmable matter. And the concept has been brewing in scientific literature since 1991, but Claytronics, launched in 2002, was the first serious engineering attempt to build it for real. Let's talk about how Catoms move, because this is where it gets genuinely clever. There are no wheels, no motors, no hydraulic pistons. The only mechanism for movement is electromagnetic force. Each Catom carries a ring of tiny electromagnets around its equator, 24 in the current prototypes. By rapidly cycling these magnets on and off in a specific sequence, one Catom can roll across the surface of a neighboring Catom. Think of it like an electric inchworm, but in 3 dimensions, with no physical parts to wear out. The Carnegie Mellon team calls this movement without moving parts. It is one of the core engineering insights of the entire project, because the absence of mechanical components is what makes miniaturization plausible. Here's something that surprised me. At the target scale of less than 1 millimeter, the physics changes completely. Gravity, which governs nearly everything at human scale, becomes negligible for a sub-millimeter sphere. Electromagnetic surface forces, surface tension, electrostatic attraction, these completely dominate. A Catom at this scale has more in common with an atom or a molecule than with a marble. So how do you test Catom physics before you can manufacture them that small? The Carnegie Mellon team had a beautiful solution. They built a giant version of a Catom, basketball-sized, and filled it with helium so it floated, a near-weightless environment right in the lab. They call it the Giant Helium Catom, and it's one of my favorite pieces of experimental elegance I've come across in any field. Then there's the power question. You have a billion microscopic robots. They all need continuous electricity. You can't run a wire to each one. How do you power the ensemble? The answer? Magnetic resonance coupling. This is exactly the same principle behind the wireless charging pad your phone sits on, but distributed across an entire 3-dimensional ensemble of Catoms. Power flows inward from the edges, Catom to Catom, at each node just enough charge to sustain the local computation and movement. No wires, no batteries to replace. The collective is the power grid. And then the software, which may be the hardest problem of all. How do you write a program that runs on a billion machines simultaneously, where each machine can only talk to its immediate neighbors, and the collective goal is to become a physical object? The Carnegie Mellon team created an entirely new programming language for this, Meld. It's a declarative language, meaning you specify the outcome you want, not each individual step. You say, become this shape. And then the language's runtime distributes that intention across every Catom, with each Catom independently computing its own role in achieving the global target. Emergence. If that word is new to you, it's one of the most beautiful concepts in all of science. A murmuration of starlings. You've probably seen the videos. Tens of thousands of birds moving as a single fluid entity across the sky. No bird is conducting the flock. No bird has a map of the full shape. Each individual bird follows 3 simple rules. Stay close to neighbors, match their direction, don't collide. The global behavior, that stunning coordinated wave, emerges from local rules and local interactions only. Claytronics is emergence by design. The entire programming philosophy of Meld, the entire hardware architecture of the Catom, is built to harness this principle, not fight it. Each Catom is a bird, the ensemble is the murmuration, and the shape you're trying to build is the sky it dances through. So where does the actual hardware stand right now? Because I know that's the question you've been holding. The current generation of working Catom prototypes from Carnegie Mellon are centimeter-scale cylindrical units, about 44 millimeters in diameter, far bigger than the final vision, but they work. Each one carries 24 electromagnets, can sense its neighbors, exchange data wirelessly, latch and unlatch on command, and execute movement on a flat surface. Since 2016, the project has expanded into a formal international research consortium. The Femto-ST Institute in France, led by professors Julien Bourgeois and Benoit Perronda, has become one of the primary drivers of the program. In 2021, their team hit a milestone they described as achieving many 3D Catoms that, quote, fit all the requirements of programmable matter. That's a working, validated 3D prototype that meets the theoretical specification. There's also a beautiful practical application being prototyped, a CAD integration system. You design a 3D object in software. The software is connected to a tray of Catoms. The Catoms physically become that object in real time. The designer pushes the digital model. The physical Catoms update instantly. Professor Bourgeois called it electronic clay you can touch. A designer can physically push Catoms with a finger, and the digital model reflects the change instantly. We're still talking ensembles of hundreds, not billions, but the scientific path from here to there doesn't require any new physics, only engineering. Let's do the fun part. What does a world with mature Claytronics actually look like? The Carnegie Mellon researchers were explicit about their #1 target application, 3-dimensional telepresence.
You wake up tomorrow morning, you walk into your kitchen, and there's no table, no chair, no coffee mug, just a pile of gray sand on the floor. You say, "Coffee table," and the sand moves, slowly. Then all at once, it assembles. Legs, surface, grain, solid, real. You can put your mug on it. This isn't science fiction. This isn't CGI. This is the actual documented, peer-reviewed scientific goal of a real project, funded by Intel, born at Carnegie Mellon University, now involving research teams across 3 continents. And today, we're going deep. By the end of this video, you'll understand not just what Claytronics is, but why it might be one of the most consequential technologies humanity has ever designed, and what's actually standing between here and there. The concept begins with a building block. They call it a Catom, short for Claytronic Atom. Picture a sphere, smaller than a grain of sand in the final vision. But inside that sphere is a complete computer. It has a processor, memory, its own power source, a ring of tiny electromagnets, LEDs that can display any color, and a wireless radio to communicate with every neighboring Catom. In other words, it is a complete autonomous computing device that also happens to be physical and can connect to other identical devices and move. Now, scale that up. Imagine a billion of these Catoms in a single cubic meter of space. Every Catom talking to its neighbors, every Catom aware of its own position. The collective billion-strong ensemble receives a single instruction: become a chair. And the collective does, not because each Catom knows the full shape, but because each one follows local rules, responds to local neighbors, and the global form emerges from the bottom up. No central controller, no foreman, pure distributed intelligence. The researchers at Carnegie Mellon had a name for this kind of material. They called it programmable matter. And the concept has been brewing in scientific literature since 1991, but Claytronics, launched in 2002, was the first serious engineering attempt to build it for real. Let's talk about how Catoms move, because this is where it gets genuinely clever.
There are no wheels, no motors, no hydraulic pistons. The only mechanism for movement is electromagnetic force. Each Catom carries a ring of tiny electromagnets around its equator, 24 in the current prototypes. By rapidly cycling these magnets on and off in a specific sequence, one Catom can roll across the surface of a neighboring Catom. Think of it like an electric inchworm, but in 3 dimensions, with no physical parts to wear out. The Carnegie Mellon team calls this movement without moving parts. It is one of the core engineering insights of the entire project because the absence of mechanical components is what makes miniaturization plausible. Here's something that surprised me. At the target scale of less than 1 millimeter, the physics changes completely. Gravity, which governs nearly everything at human scale, becomes negligible for a sub-millimeter sphere. Electromagnetic surface forces, surface tension, electrostatic attraction, these completely dominate. A Catom at this scale has more in common with an atom or a molecule than with a marble. So how do you test Catom physics before you can manufacture them that small? The Carnegie Mellon team had a beautiful solution. They built a giant version of a Catom, basketball-sized, and filled it with helium so it floated, a near-weightless environment right in the lab. They call it the Giant Helium Catom, and it's one of my favorite pieces of experimental elegance I've come across in any field. Then there's the power question. You have 1 billion microscopic robots. They all need continuous electricity. You can't run a wire to each one. How do you power the ensemble? The answer? Magnetic resonance coupling. This is exactly the same principle behind the wireless charging pad your phone sits on, but distributed across an entire 3-dimensional ensemble of Catoms. Power flows inward from the edges, Catom to Catom, at each node just enough charge to sustain the local computation and movement. No wires, no batteries to replace. The collective is the power grid. And then the software, which may be the hardest problem of all. How do you write a program that runs on 1 billion machines simultaneously, where each machine can only talk to its immediate neighbors, and the collective goal is to become a physical object? The Carnegie Mellon team created an entirely new programming language for this, Meld. It's a declarative language, meaning you specify the outcome you want, not each individual step. You say, become this shape. And then the language's runtime distributes that intention across every Catom, with each Catom independently computing its own role in achieving the global target. Emergence. If that word is new to you, it's one of the most beautiful concepts in all of science. A murmuration of starlings. You've probably seen the videos. Tens of thousands of birds moving as a single fluid entity across the sky. No bird is conducting the flock. No bird has a map of the full shape. Each individual bird follows 3 simple rules. Stay close to neighbors, match their direction, don't collide. The global behavior, that stunning coordinated wave, emerges from local rules and local interactions only. Claytronics is emergence by design. The entire programming philosophy of Meld, the entire hardware architecture of the Catom, is built to harness this principle, not fight it. Each Catom is a bird. The ensemble is the murmuration. And the shape you're trying to build is the sky it dances through. So where does the actual hardware stand right now? Because I know that's the question you've been holding. The current generation of working Catom prototypes from Carnegie Mellon are centimeter-scale cylindrical units, about 44 millimeters in diameter, far bigger than the final vision, but they work. Each one carries 24 electromagnets, can sense its neighbors, exchange data wirelessly, latch and unlatch on command, and execute movement on a flat surface. Since 2016, the project has expanded into a formal international research consortium. The Femto-ST Institute in France, led by professors Julien Bourgeois and Benoit Perronda, has become one of the primary drivers of the program. In 2021, their team hit a milestone they described as achieving many 3D Catoms that, quote, fit all the requirements of programmable matter. That's a working, validated 3D prototype that meets the theoretical specification. There's also a beautiful practical application being prototyped, a CAD integration system. You design a 3D object in software. The software is connected to a tray of Catoms. The Catoms physically become that object in real time. The designer pushes the digital model, the physical Catoms update instantly. Professor Bourgeois called it electronic clay you can touch. A designer can physically push Catoms with a finger, and the digital model reflects the change instantly. We're still talking ensembles of hundreds, not billions, but the scientific path from here to there doesn't require any new physics, only engineering. Let's do the fun part. What does a world with mature Claytronics actually look like? The Carnegie Mellon researchers were explicit about their #1 target application, three-dimensional telepresence.
We went from letters to telephone calls to video calls. Each step added a dimension of presence. Claytronics adds the final one, physical form. They imagined a media type they called Pario, where you transmit not just a flat image of a person, but their full 3D shape and motion data across a network. A Catom ensemble, on the other end, physically reconstructs a life-size replica of that person in your space. You could reach out and physically shake hands with someone in Tokyo. You'd feel resistance, real resistance, because there is a physical object there, just made of Catoms. Second application, manufacturing. Think about how absurd it is that we make billions of slightly different physical objects when one programmable object could be all of them. Your entire tool chest, every wrench, screwdriver, socket, could be one Catom mass that reconfigures for each task. Military equipment that reshapes itself for the mission. Automotive components. Imagine a car's crumple zone that dynamically stiffens before a detected impact and softens to protect passengers afterward. The Catom mass computes its optimal configuration in milliseconds. Medical applications are arguably the nearest term realistic deployment. Researchers have specifically highlighted endoscopy. A Catom-based device could navigate the body's passages, reshaping itself to fit each anatomical variation, then expanding to provide a stable imaging platform, then contracting to exit cleanly. No rigid instrument, complete adaptive geometry. Longer term? Nanoscale Catoms in the bloodstream, assembling scaffolding around damaged tissue, delivering targeted drugs to exact molecular addresses, literally repairing the body from within at cellular resolution. That's the frontier. Decades out, but the physics doesn't forbid it. And then there's the concept that makes me stop and just stare out a window for a while. The responsive home. A house where every surface, every object, every piece of furniture is a Catom ensemble. You clap your hands, the couch becomes a dining table. You walk into the bedroom, the walls reconfigure into a workspace. Your kids say pirate ship, and the living room becomes one. The entire physical environment becomes a single programmable interface between you and the world. Not a screen you look through, but matter everywhere around you that just responds. I'm going to be straight with you here. Claytronics has generated around 40 peer-reviewed publications and 10 patents since 2002. Compare that to self-healing materials, a related field which has attracted $57 billion in investment, generated 209 publications and 246 patents. Claytronics is behind the development curve. And there are 3 concrete reasons why. First, scale. The centimeter prototypes work. Making something 100 times smaller doesn't just require precision, it requires entirely different manufacturing methods. Batch photolithography, sub-micron 3D lithographic processing, self-assembly techniques, all need to be proven at industrial scale, reliably, cheaply, and repeatedly. That's not impossible. It's an engineering mountain, a big one. Second, coordination at scale. Programming 100 Catoms is hard. Programming a billion is categorically different. Meld is elegant, but at true scale, a fraction of Catoms will always fail at any given moment. The system must detect failures, reroute around them, and maintain shape integrity all in real time, all without a central controller. That's unsolved at billion-unit scale. And third, energy. A billion tiny computers all computing simultaneously, all consuming power, all needing wireless charging. The efficiency requirements are extraordinary. Current wireless power transfer has real losses. At scale, those losses become thermal, heat, which is a serious problem in a densely packed ensemble. The energy architecture for full-scale Claytronics remains open research.
None of this means it can't be done, but anyone telling you this is 5 years away is selling you something. Claytronics is a multi-decade project with a clear scientific vision and real, formidable engineering obstacles still ahead. Here's what I keep coming back to when I think about Claytronics. Every single technology you use today, and I mean every one, was once exactly this: a lab project, a theoretical concept, a piece of research that looked to the outside world like extravagant dreaming. The transistor, the internet, CRISPR, lithium-ion batteries, they all spent years, sometimes decades, in exactly the same phase Claytronics is in now. Scientifically validated concept, engineering barriers not yet cleared, world not yet convinced. Claytronics asks one of the most fundamental questions in the history of engineering. Why does stuff have to be one thing? Why does your chair have to be a chair? Why does your wall have to be a wall? The answer has always been because that's how matter works. Atoms bond, structures form, shapes are fixed. Claytronics says, what if we built better atoms? Not biological atoms, not quantum computers, physical, programmable manufactured modules, each one a complete computer and a physical object simultaneously, that together constitute a new category of matter. Dynamic matter, thinking matter. Matter that is no longer the dumb, inert stuff we've always treated it as, but an active participant in shaping the world around us. The researchers know it's a long road. They said so themselves when they launched the project. They used the word vision on purpose. But vision, backed by math, backed by prototypes, backed by a growing international consortium of serious scientists, has a way of becoming reality. Eventually. Always. The matter of tomorrow is being designed today. If this kind of deep science got you thinking, subscribe to Cipher Sci. We do this every week. We go past the headlines, past the hype, and into the actual science of the technologies that are going to define the next century. If you have a topic you want us to deep dive, something you've been genuinely curious about, drop it in the comments. I read every single one, and I pick the best ideas for future episodes. I'll see you in the next one.